Test 1, 2. Hey, this sounds pretty nice. Can you in the back hear me fairly well? Yes? No? Okay, cool. Thank you. We're just Hey, Carlos, would you call in and say that the battery is a little low on the pack here? Oh, just yeah. Test 1, 2. Test 1, 2. This one's kind of low, huh? Test 1, 2. I don't hear anything at all. Yeah. Oh, that's why I'm here. Take a look at these things. Not getting any signal at all. Now I am. All right. What happens if I talk into it? Talk, 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 talk. A little low. So let me check the levels on the microphone receiver first and make sure that looks nice. Oh, well, that's helpful. Test 1, 2. Yeah, that can go up a little bit. Test 1, 2. Test 1, 2. Test 1, 2. 1, 2, 3, 4, 5. 3, 3, 3, 3, 3. There we go. Now I'm coming in. How does that sound to the room? Test 1, 2. This is Michael Starch with the Southern California Linux Expo. We are doing a test in Ballroom A. Hey, this sounds pretty nice. Our friend in the back, how does it sound back there? Excellent, thank you. All right, this seems dialed in, so I'm happy. All right, well, thank you all, and we're signing off.
snapping, and then like these, I've never even seen someone snap this yet. And I was like, well, I know one of them was dropped.
Is this thing on? All right. Uh-oh. It's went to sleep. There we go. Have to jiggle the mouse cursor.
We have IP address parsing for humans with Jason McCall.
Thank you. Good morning. Thanks for coming out. So I'm going to talk about IP address parsing for humans. So I'll just jump right in. My name is Jathan McCollum, and I'm going to go over the agenda here. So we're going to start with just a little brief intro about me and why I'm here. Talk about what's in a network. This is just a little bit about networking basics, about how IP addresses work, how networks work, so that we can lead into how they work with code. And then we'll talk about parsing networks briefly, just some of the gotchas there, some pro tips. Then I'll talk about comparing and contrasting the libraries that I'll cover in this talk. We'll get into that in a minute. And then just a recap of what we talked about and some recommendations. I'm intentionally leaving this talk a little short so that there's time for Q&A or demos because it is a complex topic and we're not going to get into everything. So about me. So this is my second time talking at SCaLE. I think it was 11 years ago. I did a talk in the DevOps Day track when we were still at the Marriott over near the airport, talking about Trigger, which is an open source library that I wrote years ago at AOL when I worked there. But predominantly, most of the things I ever talk about are Python and networks or the marrying of the two. So I've been a core dev for numerous network automation related open source projects, one of which was Trigger that I developed at AOL. Network Source of Truth is one that I developed at Dropbox when I was there. And most recently, I was working for a small startup called Network to Code and was a core maintainer of the Nautobot project there, which is another Source of Truth project. But I've been doing InfoSec and automation for a very long time. Lots of DevOps, Net DevOps, Sec DevOps, automating infrastructure, especially managing networks, IP addresses, firewalls, that kind of stuff. So in other words, I love IPAM. And for those of you who don't know what IPAM is, it's IP address management. It's systems that are designed to manage your network objects for you. It's a big deal when it comes to managing networks because you want a consistent source of truth, right? So we'll get into that. And so IPAM is not easy. IPAM is hard. I'm sure you've all heard about IPv4, about contention, networks being exhausted. The future's IPv6, but everybody's scared of IPv6 because the numbers are really big, right? A lot of us are used to manually allocating addresses because we can contain IPv4 space in our heads, right? 192.168. whatever. It's very common in infrastructures for us to, okay, this network gets 1.1 and this one gets 1.2, et cetera. With IPv6, all that goes away. And that's largely by design. And so kind of one of the themes of this talk will be letting go of the past and embracing the future of automation. And a lot of us, I'm sure, are used to using spreadsheets and managing our IP allocations. I've spent probably years of my career migrating companies I've worked for off of spreadsheets onto automated systems to do IP address management or sources of truth. And the problem with spreadsheets is that they're free form, and you can put anything and everything in there, and that's usually the problem, is that people are bad at being consistent. Programs and software are great at being consistent. So therefore, one of the themes here that I'm driving in is manual allocation is the devil, but automation will set you free and provide a stairway to heaven. So all this is going to be Python, obviously. It's a very predominant language in the networking and tech communities as it is, but it's definitely a language that I love and very good at. So for those of you who don't know Python, hopefully it's not too scary, but you'll see these triple greater than prompts, and that means I'm in a Python interactive shell in the slides. If there are any questions or you want to see any demos, I'll jump to a terminal with a Python interactive shell so we can do a little bit of live coding or something. There's a tool called pip in the Python ecosystem that is a package installer that you would use. So anytime that we've got a package here that's installed, it's implied that it was installed via pip install. And again, this is not the most exciting content, I realize that, but so I'll try to keep it light and fun and interesting if possible. And lastly, I don't like just standing up here talking. If you have any questions at any point, please just raise your hand or stand up, and I'm happy to, I don't mind being interrupted, in other words. Gonna, like I said, leave some time at the end for Q&A, and just a little, lighthearted humor here. Obviously, the slide says one last thing, but that wasn't one thing. So we'll just get to the meat of the issue here, which is what is in a network. The fundamental premise here is that IP networks are trees, right? So you have this tree hierarchy here on the right, which is A is an ancestor of B and C. B and D are descendants of B, and you see there on the left that's what that would look like from an IP address hierarchy. This is important to keep in mind. I'm not going to go too deep into this stuff, but I'm trying to have some control vocabulary here so we can have terminology that's going to reference us to the code later. So just like family trees, we have tree terminology. So for example, your ancestors are the networks that you are descendant from, or your parents, or the parents' parents. The parent is your direct network that you're a member of. Generally, that's also where your default gateway would be. A child is, again, a direct child of a parent. Descendants are the children of all the children of a parent. Siblings is another term. I didn't go into this, but that's two objects that share the same parent, just like two children that would share the same parent. So going a little deeper, when you hear about subnets in IP or networking parlance, those are just descendant networks from a parent. Supernets are the inverse. They're the ancestors of a parent, of a network. You hear the term prefix a lot in modern day networking parlance, and effectively a prefix is just the name for a network. It's a way that networks are annotated. You also hear the term aggregates a lot. Aggregates are just prefixes. It's just another way of tracking prefixes. So just keep that in mind. When I'm talking about prefixes, it's talking about networks, it's talking about aggregates. And lastly, IP addresses are point locations on a network. And what that means is that that's where you are. And I joked in my abstract for the talk about IP meaning internet position, and that's not really what it means. It's internet protocol. But in a way, an address is your actual position on the internet, right? It's connected to the interface that your device has, and that's how you communicate with other objects on the network or other systems. One little last bit of terminology here is that there's a prefix length. This is the modern equivalent of a subnet mask. It's the size of a prefix in bits. It's how many bits are filled in the address length. A host address is what we usually think of as an IP address. That's what gets assigned to an interface. And that's a host address is an IP address or a prefix with all the host bits filled. Again, just to repeat, a gateway is how you get into a network, and the broadcast designates the end of a network. And these also have special designations in every network, right? There's starting point, the end point. And we'll cover that a little bit here in the examples. So I mentioned prefixes already. Pretty much everything is a prefix, as I previously stated. A host address is the smallest prefix. So for in example, in IPv4, a host address has a prefix length of 32 or /32. And in IPv6, a host address has a prefix length of 128 or /128. In net mask parlance, the host mask or the mask for an IP address would be 255, 255, 255, 255. That means all the bits are filled, right? But we don't really use subnet masks anymore. Right? Most everything these days is just prefixes. So that is a paradigm. It's not new at this point, but it's strange how many people, a lot of us have been around for a while and are still used to the old terminology, the old parlance, the old way how things used to be, which was class-full routing. You'd hear Class A networks, Class B networks, Class C networks, et cetera. But that actually resulted in a lot of wasted network space. And so CIDR was devised, which is classless interdomain routing. And that's where the whole designation of the network and the prefix links came from. And effectively, the larger your prefix, the larger your prefix length, the larger that number. So for example, in IPv4 32, that's the largest bit, an amount of bits you can have in IPv4, represents the smallest network, a host, which is a network of one. And then there's another thing with when we talk about this annotation, is that zeros can be omitted. So you have this ability in CIDR to have shorthand for network addressing. And this is very convenient when you work with networks all day, every day. And that's actually also helps us with working with IPv6 networks. And I'll cover that. So that's another thing called compression. It's address notation compression. So we're almost through the heavy stuff here, just talking through the terminology and the network basics. This is the anatomy of an IPv4 address. It's got 4 8-bit octets, they're called. And the entire IP address is 32 bits, which means each field can have the value from 0 to 255. And so just to go over that, so the entire internet is encapsulated as all addresses or 0.0.0.0/0, aka quad 0, or in shorthand annotation, 0/0. Many of you are familiar with localhost, 127.0.0.1. Link local, you've probably seen that on your Windows PC when you can't get an address, 169.154. And then there's private addressing, 10.0.0.0/8, 192.168, etc. But IPv6 is quite different, much bigger. An IPv6 address has hexadecimal, and it's separated by colons, similar to how MAC addresses are. And you see that it's a very large number, and which can be often intimidating. But you see here that trailing zeros here. I mentioned that compression before. This large address can be compressed to that short form you see in the middle of the screen that's omitting all the zeros. And you see this often in IPv6. And this is something that's going to be repeated here in this talk a lot. Is that's one of the elements of IPv6 that makes it less scary, because you can take advantage of this compression and don't have to worry so much about the parts of the address that don't have any bits in them. So just to recap that, IPv6 addressing is 128-bit. It's a stupendously large amount of address space. And you have 8 16-bit with hextets, as they're called. The entire internet is referred to as : /0 or just : :0. And commonly you can just refer to it as : and people know that that means everything. So localhost is : 1, and you see it's got the prefix length of /128 to indicate it's a host address. There's link local, which is FE80 : which when you look at that prefix, that's not that scary. It's only 4 characters, right? 6 characters, you count the colons. But the private address space is a very specific thing that's a little more tricky. This is also an auto-config address space. I won't go into it right now, but just put some words in your ears. The IPv6 equivalent of DHCP is called SLAC, which is stateless auto-config. I'm missing some words there, but what that does is that you actually notice if you've got a Mac laptop especially, they always have v6 enabled by default. If you look at any address on your interfaces on your Mac, you'll see an address that's FDAF, 3C0F, and so on, because your interfaces will automatically configure themselves with IPv6 addresses. That's another nice thing we won't get into here, but it's part of the magic of v6. So just one other thing, I already said this, but IPv6 networks are stupendously large. You can't even wrap your head around that network space, and that's largely in part why people are scared of v6, because our brains cannot contain numbers that are 64 bits in length, or 128 bits rather, sorry. 32 bits is a lot more reasonable, right? That's something like 4 billion and change, right? I didn't remember to put it in the slides, but you can't, IPv6 has something like 11 undecillion addresses. It's more atoms than there are in the universe, just to give you an idea. So anyway, /64 is meant to be the smallest prefix length you should use in v6, which is effectively half of the entire network space for IPv6. It's hard to wrap your head around that too, but that's what's recommended, right? You don't even get down to the minutia of these larger networks. You only care about, smaller networks. And even a /64 is orders of magnitude larger than the entire IPv4 network space, right, which is 32 bits. This would mean that that's a 64-bit network space. Again, it's more about the future of just allowing systems to automatically configure themselves and where we don't have to worry about 1.2.3.4 or whatever dotted notations there are anymore. And then there's that compressed form, right? I mentioned this already, but it's the collapsing zeros into double colons. And so this is where it kind of gets interesting. IPv4, the compressed notation is you just drop trailing zeros, right? Like, so 192.168.0.0/24 becomes 192.168/24. Quad 0, you can just refer to as 0/0. With IPv6, it's a little more complex, but you can see here, I colorized this, so you see this long address here that's 21DA and ends with 9C5A. The shorthand for that, where you drop all the zeros, you can the red, you can see that leading zeros can be omitted from any hextet. In the orange, you can see those double colons there. All of those empty zeros that are consecutive get compressed down to 2 colons. And again, the example there with that hextet that's in green, 00FF, again, you can drop the leading zeros in the notation. And this becomes really handy when you start dealing, like, that second one is the link local address space for IPv6. You see that shorthand notation is actually very concise, very clean, and less intimidating. All right. That's it for the network background. Oh, this is pretty dry, I need a water. Okay, parsing networks. This is where it starts to get fun and interesting, and have some code examples. And please, again, jump in if you have questions. Just gonna start with some pro tips here. Please use IP address parsing libraries. Do not use spreadsheets to track your IP addresses. If you are at a small company, or you're starting, or you're at a big company, and you're having a large spreadsheet, start thinking about, or start using IPM out the gate if you can. I cannot recommend that enough. Because eventually, it gets out of hand. And I've worked at when I worked at Dropbox, that was a fairly large company, and one of my major projects there was getting them off of a damn spreadsheet to manage a global network. When you're working with IPv6 networks in particular in code, never cast those objects to lists. As I had indicated, you're working with stupendously large amounts of IP addresses, and that will eat all your memory, take all your CPU, and probably kill your system unless you kill that process. And lastly, most importantly, do not ever use regex to parse IP addresses. You're going to have a bad time. And I have a whole slide dedicated to that one. So, for those who didn't hear, he said that the regular expression for IPv6 is over 1,000 characters long. Yes, it is terrifying. But so that's the thing. Regex, as you may all know, is short for regular expressions. The IPv4 regex that you've probably seen at some point in your career is, basically any number of digits separated by 3 periods. In most cases, that's probably fine for IPv4. But don't do it. Get out of the habit. Use IP address parsing libraries, right? And there's nothing regular about IPv6. And just to prove that point, to our audience member's point, that is the regex to parse an IPv6. Do not do this. It is not maintainable. It is not human readable. It is barely even machine readable. That is why we have advanced libraries that are compiled in C code that are very fast at parsing IP addresses for you. So yeah, just don't. Instead, here's an example of a concise bit of Python using the IP address library. And I just wrote a little wrapper for it because what happens is if you pass it a bad network or something it can't parse, it will raise an exception. So just catching that exception instead of returning none, which is a nil value in Python, it's just a little cleaner. So thumbs up to this code, right? This is easy to read. If you compare the previous slide to this slide, it's night and day. And this will parse either v4 or v6. That's the beauty of these new modern libraries, is it makes your tooling v6 ready out of the gate. So this is an example of using that little function that I wrote. You see we're in a Python iterative shell. So I pass it a string bogus, which is no way a real IP address network, and it returns nothing, because it failed to parse it. But all the other examples down here, you see that what happens is they get returned a specific type of object, depending on if it's a v4 or v6. This is using the IP address library. I'm going to get deep into the different libraries we're going to cover here in just a minute. But you see that last one there at the end, we passed it an IPv6 network. That's the link local address space for IPv6. And then there's a version attribute on there, and it's like, okay, is this a v6 address? And it says it is. Much cleaner than trying to do this regex thing, right? Faster too, I would argue. So starting from there, we'll talk about the fact that IP addresses are integers. Since we talk about bits, right, IPv4, 32 bits, that means any address on the network can have from 0 to 32 bits, right? Each of the 4 octets being filled from 0 to 255, that gives you every address from 0.0.0.0 to 255.255.255.255. Therefore, there's an integer representation for every single one of those addresses. So in this case, using the netadder library, and netadder allows you to just pass an integer to the IP address constructor, or the class, and you see that it returns the address 0.0.0.0. That's the default, but if you pass it the IP address version for the same integer, you see that what it returns to you is : : As I mentioned before, that's the shorthand for the entire internet on IPv6. So in the middle of the screen there, capturing 192.168/16 to a v4 variable, and then casting that v4 address to an integer, you see that we get the integer value of that network. And, well, more specifically, that would be the integer value of 192.168.0.0, the address, excluding the prefix length. And then just to give you an example by comparison, I actually picked the link local address off of my Mac here. You see it's an FE81. Cast that to an integer, and that number is something that makes your eyes cross. That's a 64-bit, or sorry, 128-bit integer that melts the brain. Furthermore, there are actually binary integers. I'm not going to go into this. This is above my head. I just trust the people that write the libraries. But bitwise math can easily be used to calculate based on an IP address and a network address, or a prefix length. Do a little bitwise math, and you get your exact network location. There are some low-level C functions that are used part of socket code that you can check out. There's a man 3 pages for those, inet Python, inet NTOP. There's numerous others, but these are the ones that support v4 and v6. That's why I mentioned them. If you really want to go deep, highly recommend those man pages. And there are some times where you need to go lower level, right? I'm not going to cover that in this talk, but the primitives are there if you need to. And so, because we were talking about trees before, right? Networks are trees. We're even in, like, the IPv4 and IPv6 are considered to be families, in that you've got the IPv4 family, you've got the v6 family. And further, your networks can be metaphorically considered to be families, right? So largely the way that family membership works, similarly just how it is with humans, where you've got your parents, your aunts, your grandparents, your cousins, your children, your siblings, etc., how everybody's interrelated to each other. Networks function similarly, in that effectively, because they're integers, if your IP address is greater than or equal to your gateway address, and your IP address is greater than or equal to, or sorry, less than or equal to your broadcast address, congratulations, you're a member of that network. So for example, 192.168.0.1 is a member of 192.168.0.0/24. And /24 is the equivalent of the net mask 255.255.255.0. Which means that there's 24 bits. That's, you think of that, the 4 octets, 8 bits each, 3 of the octets are full, so that's 24 bits. That's how CIDR notation works. It just takes the old school net mask notation and tells you how many bits there are, and you use that instead. All right, now for the most fun, this is the compare and contrast. These are the 4 libraries we're going to cover: NetAddr, IP address, CIDRize, and IP parser. So NetAddr is my favorite. It's my full disclosure. CIDRize, I wrote and maintain, so I'm a little biased, but each of these libraries do have their strengths and their weaknesses, and that's what I'm going to cover here. So NetAddr is the superset of all the tools. It's the most advanced IP address parsing and management library there is in the Python ecosystem. It's very comprehensive, has tons of utilities. IP address is pretty bare bones. CIDRize was designed to parse human inputs, so it's good for writing tools that might need to take IP addresses. And IP parser does largely the same thing, but it has some extra features or missing features compared to CIDRize. So what I'm going to do is just start with the big two, NetAddr and IP address. As I said, NetAddr is the most advanced. The catch, though, in some cases for some people, it's that it's a third-party library. That might be a showstopper for you. Some environments are air-gapped or very restrictive, don't allow third-party packages or have to approve them. But as long as you have a reasonably modern version of Python, greater than 3.3, which you shouldn't be using anyways, IP address is in the standard library, so it's very convenient. These two libraries share most features. A lot of the places where they diverge are more about your use cases, but at the base level, they do exactly the same thing. So really what it is that these libraries are more low level. You're actually working with primitives. They're not really meant for most people. It's more people who already know how networks work and who need to work with networks. And so we'll talk about some of the common features, and we're going to start jumping into some more code here. The big one here is membership. It's a very important thing when working with networks. So here at the top, this is using NetAdder as an example. This is the IP network object in NetAdder that was just imported into the namespace for brevity. But you see those first two checks there. So we've got this network address 192.168/24, which means it contains all addresses from 0.0 to 0.255. 192.168.0.0 to 192.168.0.255. So that's 256 addresses, right? So in this case, we do this little check of membership. Is 0.1 in this network? It returns true. Is 192.168.1.1 in this network? No, false. Similarly, because going back to the fact that IP addresses are integers, we can do arithmetic evaluation against two IP addresses. Is 0.1 greater than 0.0? Yes, it is. Is 0.1 greater than 255? No, it isn't. What does that tell us? 0.1 is a member of that network contained between 0 and 255. So on the left of this slide and the next couple slides, we have NetAdder. On the right, we have IP address. I'm comparing the fact that they do basically the same things. Maybe the syntax is a little different. But these are subnetting and supernetting calls. There's a lot to unpack here, so I'll kind of talk through it. And that on the top left in the first one, it's a list. So we're calling net.subnet. And so this net is actually from the previous example. Sorry, it's this one, 192.168.0.0/24. And so net2 on the right side is just the same network, but from the IP address library. So we have net.subnet 25. That means subnet this /24 into /25 networks. And what that does is it shows you that it carves them into two. I'm wrapping that in a list because by default, these calls return what's called a generator, which means it will only return the next object when you explicitly ask for it. If you cast a generator to a list, it'll create the whole list in place. You don't generally want to do this for small networks like this. For example purposes, it's fine. You see on the right, IP address doesn't take any arguments for that. The signature is quite different. So therefore, it defaults to subnetting to the next smallest size. Whereas the NetAdder library on the left, you have to tell it what you want. Same deal on the left when supernetting. You have to explicitly tell it, okay, I want a supernet of 23. If you don't do that, it will give you all of your ancestors all the way back up to the internet. On the right, with IP address, you call supernet. It by defaults to, again, only give you the next largest prefix, which is the /23. Lastly, just to compare and contrast, on the left, NetAdder allows you to do a membership test of one network object against another. You see on the right, IP address does not allow you to do that. IP address has a special call for that called subnet of. So this is what I was going into just a moment ago, which is that these libraries are almost identical except for the way that their syntax is and some of the features, but I'll cover that too. Here's some more examples. You see that at the top, this is doing an index or a slice of the network object, which treats it like a list. So therefore, if you index 0 on the network object, you get the first address in that object. Both NetAdder and IP address do this in the same way. The next line, iterating the hosts, you see the calls are different, but it's the same concept as that. That says, just give me the next host in this host iterator of this network. And so you see that instead of starting with .0, which is the first address in the network technically, but that represents the network address, the first available host address is the .1. That means in this network, 0 is your gateway and 255 is your broadcast. Therefore, .1 is the first IP, and 254 would be the last available host IP. Again, you see the next few lines, we've got the broadcast address, the prefix length, and how many addresses are contained in the network. Both libraries allow you to get the same information in similar syntax. And just a couple more examples here. There are some, call them identity methods, identity accessors of, is this v4, is it loopback, is it reserved, is it multicast, is it link local? You see that each library has slightly different parlance for those, but they largely contain the same information. So that's just more for the visual, so that you see that using these libraries is effectively swappable in the common case. So now we'll go into NetAdder specifically, talk about some of the pros and cons, and some of the key features that differentiate it from the others. So NetAdder has tons of extra utilities, like helper utilities. I'm going to cover maybe a couple of them, but not really go too deep into it. It's a very well-documented project, so the world is yours to check that out. But it has support for MAC addresses, which means that you can actually parse MAC addresses, and I'll give you an example of that. There's an IP set object for doing complex subnet math that normally would require either a calculator or some kind of advanced tooling. IP sets are amazing. An IP range, this is for doing address ranges. It's particularly useful in enterprise environments. But the cons of NetAdder is that it's, compared to IP address, it's slow. Because it's a more advanced library, it has more overhead. And again, because it's third party, it doesn't come out of the box. You have to install it, which implies your systems that you're using have internet access. Sometimes that's a deal breaker for production systems. So NetAdder has concise classes. It automatically infers v4 versus v6 based on what you provide to it. So in this case, this IP network object, of course I didn't demonstrate it here, but this IP network object easily supports either v4 or v6 addresses based on what you pass in there. One of the great features about NetAdder is you've got this info attribute that gives you some extra context on the network object you're working with. And the last bit here is you see that the NetAdder IP network object also supports shorthand notation. You pass it 0/0, and it knows that you actually meant quad 0/0. IP address objects, similarly, you can pass in an integer to an IP address class, and it will infer that it's quad 0. Or if you want to get v6, you just pass a version equals 6 argument to that. And similarly on IP, just like with networks, on IP addresses, you also have the info attribute that you can use to get a little extra context on that object. This is the best, in my opinion, is IP set. So this uses set operations, which are differences, unions, intersections, set theory stuff. It's very common in networks, right? Databases too. But so in this example, what I did is I created an IP set of 192.168/24. Created another set of 192.168.0.128/26, which is it's the third chunk of the 4/26s that make up that /24. So you would have to think, okay, where do the first two end and where does the last quarter begin? But what you can do here is with those IP sets, you just do simple differential math, like set math, like this is a set difference here using the minus operator. And what it does is it returns to you exactly the networks that would be resultant from you carving out that /26 out of the middle of this network, right? You get the 0/25, which is the first half, and then 192/26, which is the last quarter. And then just a last example there, that caret operator is a set union operator. And so I just took those two, the diff and the /26, union back together, and it gives me back the network that we started with, /24. It's an incredibly powerful feature, especially when you're working with more complex, large objects like that, especially sparse. Say you've got a really large network block and you've got all these sparse networks carved out of it. You can just throw it at IP sets and it'll give you exactly what's left. Very, very handy. IP range objects are a little more for, I would say, network administrators, more like you want to carve out a DHCP range or something, you could just have it automatically enumerate that for you. It's very handy without you having to do it yourself, right? So you could just tell it, where's my range start, where's my range end, tell me what the IPs are that are in that range. I don't have to worry about it. But you see here what I've done is casting these to a list in these both cases, because while you see that this object on the second line is represented as IP range, it actually is a generator as well, which means that it's only going to give you one object at a time as you ask for it. Casting to it a list gives you all the objects in place, which again, would not recommend in practice, but for the sake of illustration here, it shows that. More dry stuff. MAC addresses, aka EUI objects. This is another NetAdder feature that allows you to parse MAC addresses and get the actual organizational unit information out of it. That's what OUI is. So, for example, this MAC address starting with 001B77 belongs to Intel. So any MAC address starting with those is manufactured by Intel. There's a lot of manufacturers these days. The database that's in the NetAdder object, or the database that's contained in the NetAdder library does not have them all. So sometimes you'll try to look this up and you'll get an error. But it's pretty good for the common case. So that concludes the NetAdder overview. We're going to jump into IP address now. IP address pros is that it's in the standard library, as I mentioned, since Python 3.3. It is fast. It's about 3 times faster than NetAdder in almost every case. My testing is just, okay, let's try to do the same things in both libraries and just compare the timing across both of them. And pretty much consistently, IP address is 3 times faster. And there's a reason for that. This is a very bare bones library. So it's a great library for rapid prototyping or just everyday scripting, or when you don't need the advanced features that NetAdder has, especially just basic IP address validation and parsing. As I said, IP address is basic, but that's also a strength because that comes at it, you get the speed. But one of the cons here is that it's a little more of a verbose to use library if you're doing anything outside of the basics, right? If you want to get an IPv4 address, you have to explicitly use the IPv4 address class. If you want an IPv6 network, you have to explicitly use the IPv6 network class. But there's also these helpers, these 2 constructor functions, IP address and IP network. But again, the signatures for these are very limited. It only takes 1 argument. You can't tell it which version you want, so I'll cover some examples there. These constructors are helpful, but also somewhat limiting. And so here's an example of this, right? I did the previous example with NetAdder where I passed 0/0 to the IP network class, and it inferred that it was quad 0/0. You try to do the same thing with the IP address library, and it barfs at you. It gives you a value error. It says this is not a valid address, right? But if you give it a fully formed prefix length, fully formed prefix like 192.168.0.0/24, FE80::/10, it works. So what that means is effectively for v4, they don't support the shorthand notation in the IP address library. For v6, they do. So here's just a couple examples of trying to use the IP address constructor. You see that if I pass it the integer 0, it infers it's quad 0, the string. If I try and pass it the version to say, hey, this is a v6 address, not v4, it doesn't support that argument. It raises an error. But for other IP addresses that are properly formed, it gives you what you would expect. Similarly, oops, did I skip ahead? Oh, never mind. The class objects, here's just an example of using one each of the class objects, IPv4 address and network, IPv6 address and network, is that you pass it a value that validates, and it gives you the object you would expect. But again, you see here that this, because there's 4 different object types to work with, it can, if you're doing more advanced stuff with your code, it can start making your code a little more unwieldy, right? The interface for the NetAdder library is a little cleaner, a little more streamlined for development. So, lastly, there are some helpers that come in the IP address library, one of which is collapse addresses, the other one's summarize network range. I imported them in the namespace here just for brevity, but you see what happens here is they say we want to summarize an address range between 192.0.2.0 and 2.128. What it does is it gives you the smallest available network prefixes that can contain that range of addresses. It's very handy. Again, the inverse of that, collapsing addresses, is I want to take those 2 addresses and find the smallest containing prefix that would have them as members, and so in that case, /25, the 2 /25s would result in that /24 there at the end. All right, so we covered the big dogs. Now we'll cover the small dogs. These are the 2 libraries, Cyterize, the one I wrote, that's built on top of NetAdder, and IP Parser, which is built on top of IP address. And again, they share many features, but not all. These are more high-level libraries that are designed for user-friendliness. So some of the primitives that we covered here about collapsing networks or summarizing networks, these 2 libraries do out of the box for you. So we'll start with Cyterize. So Cyterize pros are that it has strict and loose parsing modes. And I'll give you some examples of that. It supports wildcards, supports bracket notation. It comes with a command line utility. And the values that you get back from it are IP network objects, which allows you to work with those if you need to. But that has overhead, right? It's a little slower. The cons, it's slower than IP Parser because it's using NetAdder. It's a little bit of a weird name, and I'm a weird guy. It doesn't support any DNS or URL parsing, which IP Parser does, and I'll show you that in a minute. And all the ranges are limited to v4, but that's the same across all these tools, because except for NetAdder allowing you to have the IP range object, because in most cases, if it's v6, you shouldn't be caring about the ranges. You should just trust IPv6 to do its thing. So these are some of the examples of how the Cyterize parser works for you. So you can give it a wildcard, like an asterisk. So I want 192.168.1.*. You see it gives you .0/24 back. If you pass it 0-15, you see that it parses that into a /28 network for you. If you give it bracket notation on the 3rd line there, you want 1.15 and 1.6. You see that what it does is it attempts to give you a network that contains those. And by the way, Cyterize defaults to loose parsing mode. I'll cover strict mode in just a second. But you see it also supports some keywords here like any. The keyword any maps to quad 0, the entire internet. Or if you pass it : it infers that what you meant was : /0 instead of the IP address : just because that's a common shorthand that, and that was really kind of the point. Cyterize is trying to do some of the heavy lifting for you. So here's some of the same examples, slightly different examples in some cases, but with strict equals true passed in. So when you say 1.* strict versus loose, it's the same thing. It's like give me all the addresses underneath 192.168.1. But you see the same thing is the case in 192.168.0-15 because the addresses in a 0./28 are 0-15. But these next examples you see here on this 3rd one where we wanted the bracket notation with 1.1 or 5 or 1.6 with strict, you see that it only returns you 2 IP network objects. And that this one's a little quirky, right? Because you're like, well, 192.168.1.15/32 is a host address, right? Well, I said before, /32 is the smallest network you can have. It's a network of one. So that's a network of one and a host address are the same thing. So therefore, you can represent an IP address or an IP network with a /32 prefix as they're effectively the same object. Not entirely, but for the purpose of the math behind it, they are. But again here, these last two examples, this loose mode of allowing you to parse a range that goes out of bounds of the network to the next network. You see here 192.168.0.254 to the next network, 1.3. This, in loose mode by default, this is like, well, okay, this is spanning two networks, 1/24, 0/24 and 1/24. I'm going to give you 0/23, which is the 2/24s. And the second example is the same value, but with strict mode enabled. And you see that it does. It gives you explicitly the smallest networks that would contain them instead of the loose, largest network that were aggregate network that would contain both of them. Lastly, there's a command line utility. So anything that you can do at the Python code prompt, you can pass it to the command line. And then but just for the sake of brevity, I've used the word brevity 3 times now in this talk, 4 if you count that one. This is verbose mode, which shows you a lot of details about that IP address network, which can be very helpful. Sometimes you just want to know, right? We can't contain all this information in our heads. So that concludes Cyterize. Last but not least is IP Parser. So this is also a very fast library because it's built on top of IP address. So, approximately 3 times faster than NetAddr or Cyterize for the same common things. Big differentiator, though, is that this returns strings instead of objects. So therefore, if you need to work with objects and you're using IP parser, you're going to have to do some extra steps to parse the ranges, parse the values, and then get objects back out. But some other nice features of IP parser is that it has DNS, URL, and port parsing support using this resolve equals true argument. I'll give you a couple examples of that. And there's also an nmap XML report parser, which I wasn't able to get working, but it's there. So I'm not going to show you an example of that, but the feature is there. I thought that was actually pretty cool. So as I had said, the cons is it only returns IP addresses. This is kind of a strength or a weakness depending on your use case. Advanced ranges, like the one that I demonstrated here on this line 3, where you see that this bottom here, where it's a range that's spanning 2 networks, Cyterize can parse that for you. IP parser cannot. Further, I was not able to get IP parser to raise any errors. It just, if there's something that it can't parse, it just passes it right through, which again might be a time saver for you depending on your use case. If you just want to, you don't want to deal with error handling, IP parser just passes it right through. So DNS and ranges, this is interesting, right? So have IP parser, pass it SoCal Linux Expo and tell it to resolve it. It gives you the IP address for it back. You pass it a couple domain names with comma separated, tell it resolve them. It gives you the IP addresses back. An example here, though, is that this last one is 0.15. If you compare that to the output from NetAddr, NetAddr gave you a /28 network object. IP parser gives you all the IPs in that network, right? So you could get those IPs out from NetAddr, but you'd have to iterate over the object that you got back versus this just gives it to you up front. Again, could be something that you need, saves you an extra step. But the last example is I was unhappy about is that you see there's that example again of that range that spans 2 networks, and IP parser is like, it just passes it through. It doesn't do anything with it. Doesn't raise an error, doesn't do anything with it. So that's kind of it for those libraries. So bringing it home, we'll cover when do you want to use NetAddr? For advanced use cases, when you have the need to calculate subnet applications, as I said, IPset's an amazing feature for that. If you have the need to manage MAC addresses specifically in your source of truth or in your network, NetAdder helps with that a lot. And as I had shown you before, if you have an IP network object or an IP address object from NetAdder, you also have this info attribute that gives you some extra metadata about the network objects, which the IP address library does not do. That's also can be very handy. When you'd want to use IP address, when performance matters. Say if you're processing a large amount of networks on a global backbone or a very large data center or large enterprise environment, that 3 times speed cost that NetAdder has over IP address might make a difference, especially for common use cases, right? There's a lot of commonality between those libraries as I illustrated. You might not need all the advanced stuff that NetAdder has, and IP address is fantastic for that. So quick and dirty solutions especially, and I've repeated this multiple times, but if you can't use third-party libraries, IP address is always there for you when you need it. So I guess another 2 cons of Siderize and IP Parser obviously is that they're also third-party libraries. I just realized that right now. So when would you want to use Siderize? If you have user-facing applications where you want to take IP addresses as input, that is what I initially wrote Siderize for. It is for user-facing apps that you want to validate. Is this a valid IPv4 address? Is this a valid v6 address? And just not even let the program proceed past that. So when you need a lot of flexibility in user inputs, right? Because Siderize does have some heavy lifting features that it's done for you. Or we need that SCaLE utility that I showed you. Very useful. And then when do you use IP Parser? When performance matters, similarly to an IP address. When you're parsing user input, but you need to do it at high performance or high scale. When you need to resolve DNS easily without having to think too much about it. And again, if you're using Nmap, you need to parse XML reports. IP Parser will do that for you too. So that's it. We came in just under time. So I just wanted to recap here with the libraries that I represented here. That's their where you can get their documentation, or in the case of IP Parser, it's the GitHub for it. So NetAdder's got its own docs. IP address is just part of the Python 3 standard library. Siderize has its own docs. It's also on GitHub. And IP Parser does not have its own published docs, but it's got a nice README on GitHub. And if you want to look me up, I'm Jathanism on all the things, GitHub, Twitter, Threads, whatever, Reddit. And nobody jumped in except our friend down here who commented on the regex for IPv6. But if you've got any questions, if you want me to demonstrate anything, I'm happy to. We've got a little bit of time left. Yes? Well, yes, they will. I'm sorry, I didn't upload them before the talk, but I was doing last-minute changes. So yes, I'm going to upload them right after the talk, so they'll be available on the SoCal Linux Expo website. It is, I know. It was kind of dense. Right.
And when I did recognize them, I wanted to get the smallest number of rules. So the Cedar address, I wanted to have a slash with a number following it that would capture full ranges. And eventually I got tired of China. It just got me tired of Chinese IP number range.
Right.
Then I got rid of that when the customers told me they were going to China. So are there any tools, or is there any interest in developing tools that take an IP range, just a single list of IP numbers, and change them into the smallest number of procedures, where you can allow, oh, there's 5 IP numbers that weren't blacklisted,
Yeah.
but because the slow and low attacks, where they're doing one every day for 400 days, but they're coming from 20 IP numbers, so they're actually doing 20 attacks a day from different IP numbers. That's what I want to block.
Yeah, I would say, so the question was, are there tools that allow to aggregate disparate sets of IP addresses under one aggregate? And I'd say Cyterize actually would do that for you. That's the tool that I wrote that's on top of NetAdder. You can give it a sparse set of addresses, and it will, there's one I didn't really show you, but there's one called Optimized Network Range. Let's see if we have a little second here. Oops, it's Cyterize. So can you, oops, you guys can't see that. I need to move that to the other screen. Can you see that okay? Oh my goodness, I can't see it now. I should probably change to screen mirroring here. Let's do that. Hopefully this doesn't just cause an issue here. Well, anyways, there's a, I'll just do it here. It's Cyterize Optimize Network Range. Yeah, so here we go. Like, this is just one example, right? We've got a range of IPs here, and you give it a threshold, right? If you don't default, what it does is it just gives you, okay, I'm just gonna try to turn them into something, but if you give it a threshold, say 0.5, it gives you just the entire network that contains them. So that's kind of something you're looking for, right? Yeah, it is kind of magic, right? But there's also a library out there, I think it's called like Aaron Parse or something like that, and Aaron's the registrar for all network assignments globally. And so they have the who is information on the IPs of like who owns this prefix, right? So there's a Python library that will actually give you that information, so you don't have to look it up yourself. It's very, very convenient. So it's like you could probably marry 2 of these libraries together. 1, collapse the prefix. 2, look up the prefix and who owns it, right? And then track that in your internal system.
If only the whois database didn't restrict you on the number of whois queries.
That's a separate problem. Yeah. Right. Any other questions? Yes. IPv5, any of the odd numbers in protocols are experimental. So that means that even numbers 4, 6 are stable, right? So the idea was before IPv6, there was IPv5, and it's like kicking the tires on, okay, where do we go from here? And effectively the decision was, well, let's expand the address space so we never have to solve this problem again. That is IPv6. And I mean, when I say these numbers are stupendously large, right, it's like a 128 integer space it's more atoms than there are in the observable universe. So therefore, we're likely never going to run out of IPs, at least until we start, becoming Star Trek civilization. Yes.
So you mentioned transitioning companies or helping transition companies off of spreadsheets. What do you do when the network admin team is not comfortable with Python? Are you just providing a CLI tool for them?
That's a tricky one. Yeah, it really depends on the environment, right? When I worked at Dropbox, I had the luxury of it was a Python shop. Everybody used Python. Oops. With some other companies I've had, there's the adoption problem, right? You have to be patient. Python, fortunately, has a low barrier to entry, right? I think that's why it's become so popular, is it largely reads like pseudocode. But I think the challenge there is trying to provide tools that have polish, right? So there's some of the other ones I mentioned, right? The network source of truth was also something I had developed while I was at Dropbox, and that's meant to be it's got an API, it's got a web GUI, it also has a command line, but the goal is that it's got different interfaces for different audiences, so that, okay, we can provide the enterprise team who might not necessarily be as tech savvy as, say, the engineering team, or, you know, not as code savvy, rather, provide them the web interface. Maybe another team that wants to integrate, like the data center engineering team, they can use the API, right? And I think that's really the challenge when it comes to doing things in large environments, is you have to think about how your other people are going to be using your tools, right? So it's never going to be one-stop shop. Yes?
How long did it take you to write the optimize algorithm? I was attempting it, and after 2 weeks,
I don't remember. So the question was, how long did it take to write the optimized algorithm for Siderize? I don't really remember. It was a while ago. It's been pretty stable, and it's tested. It's got unit tests. It's actually not that complicated. I think really what it's kind of leaning on effectively a calculation of how sparse the inputs are compared to, actually, it's a little bit of both. One, it's parsing and doing a little bit of a calculation based on the threshold you pass it. But I think actually, if I remember correctly, it's leveraging another function that's part of the NetAdder library core, one of the utility functions I mentioned but didn't demonstrate. I encourage you to check the code out on GitHub. Yeah, absolutely. Yes? Siderize does. Siderize will let you do wildcards with some limitations. Otherwise, no. Like I said, NetAdder and IP address are both more low-level libraries where they're expecting you to be a lot more explicit. But there are some tools in the toolkit there. Siderize is probably, if you want basic wildcards, it's probably the best starting point. Varies. Yeah. Any other? Yes?
So the implementation for the two libraries probably don't rely on regular expression, the parsing and
They're actually not. So what they're doing, they're underneath the hood, they're actually using the C system calls for, I mean, the Siderize library that I wrote is using regex in a couple places just to identify if you've got hyphens or asterisks or brackets in them, things like that. But ultimately, it's just verifying those and then passing it on to the underlying library. But there's C calls. I mentioned the reference to man page that you could look at. It's the inet calls, inet pton, inet ntop. And that's basically the calls that allow you to say, take an integer representation of an IP address and turn it into a string human readable representation, or vice versa. Take the string representation and then turn it into an integer. So therefore, if you have an invalid string representation and try to cast it as an integer, you're going to get an error, right? So therefore, it's not a valid IP address. And so therefore, those calls are actually pretty fast because there's system calls in C libraries. The slowness is in the veneer and the abstractions we put on top of it to make the Python library very user-friendly, or as user-friendly as reasonably possible.
do you have any libraries with code that do IP6 or
Yeah, all these libraries I demonstrated, they all support v4 and v6 out of the box. That's why I'm recommending them, right? It's like you can start your next generation tooling today. You don't have to branch your code. You just start using a modern library, and you can parse both addresses out of the box.
Since you're far more expert than I am, when will the IP4 addresses become depreciated or obsolete?
So the question was, when is v4 going to become fully exhausted or obsolete? I honestly think we're never going to get rid of IPv4 because it's so convenient, right? Even especially at home, like I feel like there's always going to be maybe decades from now when it's just gotten to the point, because I said the IPv6 has a lot of features for automatic configuration, and you see this with Macs. That's what's nice about Apple ecosystem stuff is you have a bunch of Macs on the same network. They automatically configure and talk to each other via IPv6 without you having to do anything. That's awesome. Like your printer, you just plug your printer in and it just works. You don't even have to configure it, right? And that's the promise of IPv6 is that as more companies and more people get accustomed to it, some of these old school things like, okay, I care that my finance segment is 192.168.1.0 and my business segment is 192.162.0. It's like you don't care anymore. You just let them automatically configure themselves. And so I think that, you know, like I said, likely decades from now, we probably won't ever have to think about or care about IPv4 anymore. But for the foreseeable future, especially while all of us old timers are still alive, it's not going away.
Keeping your internal LAN secure with an unroutable IP4 network.
Well, you know, it's interesting. So what he said is keeping your internal network secure because of IPv4 numbers or non-routable. There are non-routable prefixes in IPv6 as well. They're not necessarily private. That's the whole idea there, is that privacy is really an illusion anyways. It's more about access control, right? Is there another question? I saw some. There's not. NAT is obsolete as well. Yeah, so the question was, is there NAT in v6? And the answer is no. And the reason why is because there's so many IP addresses, just use your access controls like access list firewalls, etc. Don't worry so much as NAT as a security feature. NAT was never actually designed to be a security feature. It's more of a side effect of, that your private addresses are kept hidden from outsiders. But in the reality, when you actually inspect the packet payloads, you can always see the real source address. So, like I said, it's an illusion. So, any more questions, comments, concerns? Well, thank you guys. Thank you for the engagement. Yeah, one more. I don't know off the top of my head. Yeah, do I still have it up here? What I'm referencing is back here. Oh my gosh, it's so far back. Did a lot of slides. I'm very sorry. Is it here? There it is. Right there. FDAF, 3COF, etc., etc. Right, it's a mess. I love link local, FE80::, that's easy. But yeah, the private addressing is really meant for say, it's non-routable, right? Similar to how in that BGP won't accept those routes. BGP on v6 won't accept those routes. Yes, thank you. Thank you for all the questions.
Oh, great. Good timing. We were just trying to figure it out on our own. Everything? I mean, just. I don't think so.
Do you have any computer audio?
Nope. Oh, I do have audio though. It looks on.
Is this your presentation?
Yeah, it is.
Okay, you might have to, what is it about like dragging it over? Yeah, because it's not.
Okay.
Okay, you can like unfull screen.
Okay.
And then, do you want to just.
Ah, look at that. All right. And then, perfect. Great. Thank you so much. No, I don't think so.
There's no audio from the coming up from the computer.
That's fine. No, I don't think so. Is this too loud? Okay. I feel like I'm screaming. Okay. Absolutely. All right. We're 1 minute off. So, yes, I'll tell you, I wrote this talk for my dad, and I just left my dad at the hospital. That's where I am right now. Yeah, the previous of my talk was, well, I started out this talk to learn more about conventional commits because we use them. I work at UCLA Library, and we've been using them for, I don't know, a couple of years now, or maybe a year. A lot of our projects we converted over to using conventional commits, and it's been a total boon to. I just have to check this because I told Lars my husband not to text unless it was an emergency, and he just said turn off the phone. So anyways, I wrote this talk for my dad so he wouldn't be bored sitting here, and I thought, it's Sunday, no one's going to show up, but you're all here, and I'm going to take a picture of you so I can show my dad later. And so smile, please. Thank you. So bear with this talk a little bit because I started out, I changed the name of it to the lexical semantics of Git. So it's from Git add to conventional commits. And lexical semantics is the practice of deconstructing words. I have to look at this because this is basically my talk here. It's deconstructing words to understand the meaning of things in terms of context. So it's breaking down words into their core. So it's about Git concepts from the beginning. So I assume you all use Git, right? So this might be a Git talk for your children or your grandparent or your parent, or I think it's pretty anyways. It's the A to Z to Git, but not quite it's the A to M of Git because we all know Git is incredibly complicated. And let's see, okay. So the vocabulary of Git, there's a lot of vocabulary in Git, right? When you're starting out, there's so much Git stuff that you have to learn that as a beginner, you can imagine it's overwhelming. So the first section, we're going to go from beginning to intermediate to advanced, but really just the concepts and lexical breakdown of Git's vocabulary. So the first three are Git, GitHub, and version control. Using Git and GitHub, you create your code on your computer using Git and GitHub for version control. So the first question is, what is Git? Git is, I didn't really know this, that it stood for Global Information Tracker until I looked this up. Git tracks information, and Git is version control. We all know that. We use it every day for version control. How would you explain version control? Well, break it down to its root at version, and a version is just something that's different from other things of the same form. Version control is a way to track your changes, and Git is just a version control tool to track your changes. Git is version control. There's your version 1, our cute little rubber ducky that we all talk to, and here's version 2, our green rubber ducky. There's version 3, you've added a little something extra to him, and version 250, we now have a peacock. And you can always go back to version 1. Well, not that anyone really goes back to version 1, but you could, theoretically. So Git is a tool to track changes locally on your computer. If your computer happens to set on fire, all your changes are gone forever. That's why we use GitHub. And what is GitHub? Hub is the central part of a wheel from which the spokes radiate. I'm a bicyclist, so I chose this bicycle hub. So the hub is also the center of an activity, region, or network. So GitHub, aptly named, is a centralized place to track your changes. It's an online platform where developers can create, store, manage, and share their code. And it's in the cloud. So GitHub is version control, Peacock, from rubber ducky to peacock. It's a way to track your changes. It's a way to track your changes on the internet. So when your computer sets on fire, which sometimes it does, all your changes are saved forever. And as we know, some are saved to the Antarctic. Who has Git in the Antarctic? Yes, and probably in space now too. I heard they brought the microfiche to space, so it's pretty cool. It is pretty much forever. And this is the GitHub, what GitHub looks like. That's my GitHub page. And the benefits to using GitHub version control is creativity and experimentation. You can experiment with your duck as much as you want and go back. You can securely save your data in case your computer catches on fire. And you can collaborate with other people and share your ideas. You can collaborate on one-on-one to do a project. You can collaborate with a team of people, and you can collaborate with people around the world. GitHub basically equals community. You can work together, share ideas, keep track of changes, and secure your data. So here's our vocabulary review. Now you can explain Git. Now you can explain GitHub. Now you can explain version control to your child and your parents and your partner and to anybody. Next up, new vocabulary. We're moving on to all the commit stuff, the Git workflow. So a branch is like a branch of a tree. That's where they got it from, I assume. And this is your main tree and branches, or it's not the best, but the roots of the tree is the main. And then when you make a branch, you get the exact same tree. Not really a branch, you get the exact same tree. So that's main, and then your branch looks identical. So you get the same rubber ducky. And from main, you do git checkout your branch name, and then you have a branch named update duck's color, whatever you want to name it. You make your changes to your branch. This is sort of where the branches look like on GitHub over there on the left. And the next concept is the repository. So the repository, the word just means a place, a room, or a container where something is stored or deposited. like a bank where your money goes, or that little box where all those kitties are stored, all the octocats are stored in the GitHub's box. Your code is stored in a repository. You have a local repository on your computer using Git. You have your remote repository online using GitHub. And as we mentioned, that your GitHub's in the cloud, so in case your computer sets on fire, it's safe. And all your repositories are in GitHub, and this is sort of what they look like there. So next concept is a commit. A Git commit, is to bind, that's just a commit. A commit is to bind or obligate by pledge or insurance. I commit myself to you to show up to this talk. That's why I'm here instead of at my father's bedside. So the latest changes that you're adding to your, so GitHub is the latest changes that you're adding to your repository, or I added the next slide. So we all know what a commit is. The commit is what you add to your repository, and you make your changes there. So your Git workflow is a series of activities that are necessary to complete a task. That's what a general workflow is just any kind of workflow you have, whether it's to clean your house or to rake your yard. You have a series of tasks. The Git workflow is, at its most basic, is you make a change to your code, you add your code, you commit your code with a message, and you push your code to GitHub. I suppose you don't have to do this last thing if you don't want to save it forever, but if you do, and you work on a team, it's your best bet. So back to step 3, and when you commit your code with a message, you use a commit message. So the commit message explains the changes that you made to your project. The commit tells a story of changes over time. The commit message should complete the sentence, when I add these changes, it will blibbity blub. It will, what have we done here? We have, Eric, what did we do?
We changed the color.
Right. So when I add these changes, it will change the color to the duck, or add a hat to the duck, add the sunglasses, add 2 wings to the duck. Generally, like, you add a verb and with the generalized thing of what you're doing, if you're just doing a very simple commit. So here we have change the color to the duck. So back to the Git workflow, you commit your code with a message, and you push your code to GitHub. So let's review. If you're not asleep yet, add commits with your commit message and push your changes from your local repository in Git to your remote repository on GitHub. 1, 2, 3, 4. So then you are sharing your thoughts and ideas with your team and the world. And our vocabulary review, now we know Git, GitHub, and version control. Repository, local remote, add, branch, commit message, Git workflow, and push. Did we cover push? Yes, we did. So that's quite a decent amount for a short time. New concept. So pull request. So a request is just asking for something to be done. I asked if I could speak here. They said, sure, Jen. So a pull request is a method of submitting contributions to a project. It's also a proposal to merge a set of branches, changes from one branch into another branch. Usually you're merging into main. Usually, not necessarily, but it's usually the case. So you're asking the question, can I change the color of the duck, please? And you use a commit message to submit your pull request. And your commit message says, change the color of the duck. And this is within your Git workflow, is your pull request. And a pull request, is this actually a pull request? Yeah, this is a pull request. We have, in my team, we have and I'm very particular about our pull request. This is a very old pull request I did, where it's just super simple, but generally connected to ticket and what you did. It's nice I really like to leave comments and messages in the commit message to be super clear, and you can use Markdown, which is, it's nice to be clear, so at least your future self will know what you did if, if no one else looks at it. Here's another pile of old pull requests from, I don't know, 2013, and even more. Okay, so these are guides to write good pull requests. Oh, there are guides to write good pull requests, commit messages, and branch names. The main thing is to make them meaningful and agree on the format with your team. And it's definitely best to use the standards of the community, or people are going to mock you mercilessly, as we all know. So the new concept that's next is the merge. So merge is to combine a form or a single entity into a single entity, right? So two things become one. So our branch and from main and your branch change duck's color turn into one branch that is just main. And there's your pink duck and your green duck, and you say your commit message, change the color of the duck, please. And yes, you can merge your code, and once it's merged, then we're all happy, and the changes are accepted, and the branches are merged, and you have your green duck is the main branch now. So the next concept is what we all hate, is the merge conflict, right? They can be very complicated, and sometimes it's better just to make a new branch. But you know, at its most simple, and sometimes it's nice and easy, you just make your choices and decide which duck, which color you want to keep. This is a pretty nice, simple change. So both branches make changes to the same thing, and you have to decide which one you want to merge to main and keep in main, and we decided we're going to keep our duck green because happy St. Patrick's Day. So now we'll review the vocabulary, blah, 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 and pull request, merge, and merge conflict are our new ones. So now we're all the way up to intermediate. You still with me? Thank you. The semantic versioning. So who uses semantic versioning here? Pretty much everyone, right? Because it is a standard. So the semantic version, just semantics, is singular, but it looks plural, right? But it is the study of meaning in language. So commit messages tell a story. Semantic versioning tells a very specific story. The story helps you keep track of your changes. The story gives your team a standard to work with when you're doing your versions. Semantic versioning is the standard that the community uses all over the world, right? Since Semver, I don't know when was Semver invented or proposed, a long time ago. So semantic versioning is 3 sections: the major, the minor, and the patch. The major is incompatible changes, like when you say, oh, this is version 1, version 2. Minor is changes to functionality that are just features generally, and things that you can are compatible with your version. And a patch is basically bug fixes or chores or styles or performance fixes. There's our major, and is the patch. Oh yeah, look at me. Changes to functionality is that's a minor patch and a minor and a patch. And okay, this is more explanatory. Here's our patch. We've just changed the color of the duck. That's pretty minor. No one's gonna be sad. Let's see. This got a little garbled here, sorry. Okay, so that was the patch. This is the change to functionality, right? That's pretty different. This is not the same duck. This is a very different duck. His function has changed. He's now like doubly floating, and he has a hat, and so that would be a minor patch, and you would keep the patch version as well, because we haven't updated the major version yet. So this duck has changed so much, we really can't go back from the killer duck. So once you get to this point, you have to just change it to version 2. Everything resets, the minor patches and the minor and the patches reset, and you just start all over again. And you move on from there, because it's incompatible at this point. So that is our vocabulary, our new vocabulary, which is the semantic versioning, minor, major, and patches. Next, we have our changelog. Change just means to make something different. I changed my outfit only 2 times today. No, really, I didn't. And a log is an official record of events. So a changelog is just the log of notable changes made between each release or version of your project. I don't know if you use changelogs, but we use changelogs, and we use GitHub Actions to create our changelogs now. So we don't even have to write them, which is much nicer. But it's nice to have a record and a log of your changes over time. You can see there's our semantic versioning at the top and the date that it changed, what changed within it on that date, and a message about it, and as well as the ticket number and the pull request number with links to them, so that you can always see what they're connected to if something breaks, which is really the only reason you need them. So these are the types of things that you might see in a changelog. All these different things, change the colors, that you added things, that you're delivering software, that, but face-to-face, I don't know what, oh, that's from an old slide. Sorry, I copied these from an old talk. So issues are the next topic. The topic, an issue is a topic to be thought about, right? Like if you have issues with your friends, and you have to talk it out. So you have to think about it, and you have to talk it out. GitHub issues track tickets, ideas, feedback, tasks, or bugs. If you've worked in open source issues, people submit issues so that things can get done. People submit ideas, they submit feedback about things not working and bugs that they see. And when you work on a team, you can use the issues to track tickets. We've done that when we were creating components. You can either use a work tracking tool like Jira or whatever, or Pivotal Tracker, or whatever you want to use. But GitHub issues is a nice place to track your issues as well, or your tasks, because then you can link all your other GitHub PRs there very easily and close it automatically. Next is template. So a pattern used as a guide to make something. So like you have a template for a cookie, making a cookie. You have your cookie cutter. So we can make a whole bunch of cookies because we have a cookie cutter. So we use templates in GitHub to make all sorts of things. You can create a template that every time you create an issue, you can create the same template. So we use this to create issues to make components. So every time an issue is created, like create new issue, it comes up and you can fill in the blanks of all the info, like what are we calling this? Every single thing, anything you want the issue to say, you can make it say. You can have, what else can you do with issues? You can have help if you want, this is a really good one. You can have your pull requests have a template. So we also use that, so that it enforces people to write like that it's connected to a ticket, and you have your PR that it's linked to, and everything's laid out so that people can fill in the blanks so that people don't get lazy about making their commit messages. because we all know we get a little lazy when we're working fast. So our vocabulary has expanded into changelog issues and templates. Now we've reached advanced. This is like when you go to the ice cream store, and if you can eat all this ice cream in an hour, then you get a free ice cream. So you all get a free ice cream. Or maybe that was just Friday if you were here. So release. So release is to make something available to the public. And a GitHub release is a way of packaging and providing software to your users. So this is our release, and this is using our semantic versioning again, and as well as GitHub Actions and a plugin that, so our releases are written, we don't have to write them anymore. We used to painstakingly write them, and I set up a whole Confluence page of how I wanted them written because I would get very fussy about people writing it wrong. And now they're automatically written, even with the emojis, which is just makes it a little more fun to look at, all right? So the bug has the bug, the chores and the updates, and it shows the contributors, it shows what happens. And the cool thing about releases is that, and this has happened to us on many occasions, is that when you have a release and you push your release to production and something goes wrong, you can just go back to your old release and push that old release to production and figure out the bug, and your site's still working. And everyone's happy, for at least for a little while. So conventional commits are, a convention in general is an agreed upon way of doing something, right? Like the convention hall. Oh, that's not a good one, is it? What's a convention? Someone. Driving on the right side of the road. Oh, driving on the right side of the road. I like that, yes. Okay, so conventional commits is a set of rules to follow to write your commit messages. So does anyone use conventional commits? I do. Yeah. We worked with a developer in Brazil for a little while, a young guy, he was like 20. He came onto our team and he started writing his pull requests, and I was like, that's not how we do it. We write it this way. And he was actually writing conventional commits, and we hadn't used it yet. And then our UX team had adopted conventional commits, and so it developed from there. And their commits were just so beautiful looking, and their pull requests and everything, we decided to adopt it for our projects. So conventional commits combine your commit message, your semantic versioning, and your pull requests. Instead of writing change the color of the duck, you would declare what type of change you're making. So the color, so there's a bunch of available types. There's feet, which is a new feature. You have to write, and I didn't put this slide, but you have to write the type, colon, and then your message after that. You can write in brackets before the colon some other more contextual words, but the basic structure is what you've done, what type of thing it is, and then your message, your general commit message, like change the color of the duck. Then other available type is fix, which fixes a bug. Docs, documentation only. Style, changes that don't affect the meaning of the code, like our duck would be style. Styles, white spacing, formatting, missing semicolons, stuff like that. Refactor, a code change that neither fixes a bug or adds a feature. Perf, performance, which is a code change that improves the performance. Test, to add missing tests or correcting existing tests. And build, changes that affect the build system or external dependencies, like gulp, broccoli, npm. Those are obviously JavaScript things, but of your choosing. CI, continuous integration, changes to our continuous integration configuration files and scripts, like Travis, Circle, Browser Stacks, Sauce Labs. Chore, other changes that don't modify source or test files. You know what a chore is. It's a chore. That's why it's called something like that. Revert, something that returns to a previous commit you've done. And this is how our pull requests look now. So you can see it tells a story. Like we generally have been using mostly fixes, chores, feature, CI. Like you kind of get to see, oh, we're doing a lot of the same thing over time. And it makes it kind of easier to screen when you're looking at it as a whole. So actions, it's the process of doing something. GitHub actions allow you to automate your build, test, and deployment pipeline. Conventional commits with the GitHub actions, that's where the magic happens. That's like conventional commits on their own, they're pretty, but GitHub conventional commits with GitHub actions, it's very powerful. You can use the types from your semantic commits to create workflows to do things automatically. And automation is the key to developer happiness and DevOps happiness, or probably not, but DevOps happiness a little. You can create workflows that automatically test your code, that automatically release your code, and that build and deploy your code to whichever environment you want. And you can choose which of your semantic versioning triggers those cycles. So these are the ones that we're using here on the left, the actions we're using like to manually rebuild and deploy and to release. And what I've realized that automation is magic, but you can use it in multiple different ways. Like 3 of our different projects are using the semantic versioning with the semantic versioning with the GitHub actions in completely different ways. Like you can even test your pull requests with the GitHub actions. Like when we submit our pull request, you can set it to check that you've checked your title, that your title has a semantic version in it, that you have a label set, that you've done all your tests are passing. You can use it for deploy, like I said, and yeah, you can use it to automatically trigger pretty much anything that's within the the conventional commit workflow. You can set it up at your pleasure. So our vocabulary has really expanded. And I will say, as closing, that lexical semantics is the key to understanding the concepts of many things, including Git and GitHub, and why they exist. To share ideas, to work with other people, to work with a team, and to work within the community. Thank you. I don't know if I can answer any questions, but I could try. Yeah.
Well, just a comment was great. I had no idea Git stood for global nation.
Me either. Yay, you learned one new thing. Yay. Yes. Yeah. Yeah, it's been nice for our team. We've really enjoyed it. Yes, Ashok.
For the things that are marked, so I saw for features that you have like a ticket number associated with them.
Mm-hmm.
In your system, do you also mark things that are like chores or CI or any of those? Are they also created as tickets in the system for tracking, or do you just
Yeah. Yeah, that's part of the semantic, I mean, the conventional commit types is chore. Like, I think what we have set up is like our build only, the release only gets made if you, well, things are automatically merged in one repository if it's accepted, if it's a feature, if I think just features, and then if it's labeled a bug fix or a chore, it doesn't automatically build the release. It waits, lets them build up, and then once there is a feature associated with that collection of commits, then it will automatically build a release. But it doesn't have to be like that. You can set it up in the Git workflow however you want. Yes. Conventional what? What I like to do is we use Jira for tracking. So I always put the ticket number and then underscore, and then the name of exactly what it says in the ticket, so that it's really easy to go back and find the ticket. So that's how I like it, because we push our tests to Parsing that takes a snapshot, and so when we run the Parsing commits, it has a list of the branches that have run tests. So so you have to find the branch to press the button to run the test, and if you don't put the ticket number, it's super hard to like. It's just annoying to like find the stupid branch name. So I don't know, that's what I like to do. Or I guess if you don't have ticket numbers, you can always write I used to write my initials first, and then generally kind of exactly what you're doing, like change the color of the duck. The same thing that my PR message would be. I would do that. That's, yeah. When I write the commit message, yeah, like for the PR, the commit message for the PR, yeah. Yes. We have a format that I set up. Yeah, it depends on the repository and what we're making. Like we have them set up differently for each repository and what we kind of are doing for there. So some of them is like, did you release it here and check it? Did you release it here and check it? Kind of a checklist, so that we got this from Funk House. We worked with Funk House, and they work with outside vendors, so a lot with outside developers. So they had a really tight checklist of like, how long did this take you? Did it work here? Like, does it look like it's supposed to look like? Is it did all the tests pass? So there's those checks, and so we adopted some of those, and then we also always put a link to whatever ticket it came from, so that you can find it later. And then I generally take a snapshot of it working, and put the snapshot in there, and kind of put any notes of if anything else needs to be done later, or any other notes that could help future me or anyone who's reviewing the ticket that would help them merge it. So if you're like, okay, I added this code, but when I saved it, for some reason, all the text got rearranged, and so the pull request looks crazy, but I only made this change, and this change. So when you look at the file changes, you're going to see it says too big to look at. It's like, and it's not. I only did these three things. Look at this line, and this line. That's what I like to do.
All right.
we know what the little octopus guys are about?
It's the Octocat. I love the Octocat. I don't know. Well, I heard that the person who made the Octocat only got paid $200 for that logo, which, all right, it's the story of being an artist. But let me see, I'll go all the way back to the top. I made my own Octocat, so I think it has something to do with, yeah, there's a lot of slides. I think it has something to do with it has multiple tentacles, right? So it's kind of its own hub, right? That's what I think, it is a hub in itself, an octopus, right? That's the one I made for myself. And I think you can, I made it in Illustrator, but I think you can, there's a website you can make your own, because you saw all those awesome GitHub stickers. Oh, which I meant to bring, but I forgot. Yeah, any other questions? No matter how basic or advanced, I don't know. All right, well, thank you so much. Thank you. Yay.